Welcome to Maths with EJD. In this video, I'll be talking about special cases in Simplex method. In fact, this is the third video in that series. So I always like to remind you of the special cases. So the first case is degeneracy, which we have already dealt with. Then we've dealt with alternate optima, alternate optima. Okay, dealt with in the last video. So in this video, the focus is going to be on unboundedness. And after this, we'll be talking about infeasibility. These things actually seem to bear resemblance with what we had for the graphical method of solving linear programming problems. So infeasibility is coming after this one. So our focus for now is on unboundedness. Unboundedness. So what do we have to say about unboundedness? An unbounded solution, an unbounded solution arises when the objective function can increase indefinitely, without violating constraints. Without violating any constraints. Okay. Now, this usually occurs. This usually occurs when the feasible region is open-ended in the direction of optimization. In the direction of optimization. Okay. Now, let's take an example of this situation. Example, imagine that you need to maximize z equals x1 subject to x2 is less than or equal to 2 when x1 minus x2 is greater than or equal to 1, with the non-negativity constraint that x1 and x2 are both greater than or equal to 0. Of course, this is the canonical form. This is the canonical form. And we have to change it to the standard form so that we can use simplex method. So standard form now. So the standard form here definitely is going to be maximize z minus x1 equals 0 based on what we have up there. And then this is subject to x2 plus s1, all right, is equal to 2. X2 plus s1 is equal to 2. Now, normally here, right, we have x1 minus x2 greater than or equal to 1. So we need to introduce a surplus variable. This is slack variable. So we need to introduce a surplus variable now, such that we now have x1 minus x2 minus s2. So we need to subtract something from this so it can be equal to 1. And that is actually a surplus variable. So then maybe an artificial variable would have been necessary in addition to that if we won't be able to get a feasible solution to proceed. But I mean, if we can get a feasible solution, we'll just move on with this. So now we have the non-negativity condition that x1, x2, then s1, s2 are all greater than or equal to 0. So the next thing is to set up the initial simplex tableau. Okay, we set up the initial simplex tableau. So initial simplex tableau. The first simplex tableau is called the initial simplex tableau. And just like I introduced I think in the last two videos, right? Instead of having a full-fledged table, you can just put it in matrix form already, right? Just put it in matrix form. So you have BV. So the non-basic variables definitely will have to be the surplus variable S1 and the slack variable S1 and the surplus variable S2. Of course, you have your Z coming beside this. So you have it in a form of matrix straight up. And then this is like X1, X2, S1, S2, and then you have your B. So X1, X2, coming here now, X1, X2, X1 definitely has a coefficient of 0, X2 has a coefficient of 1, S1 coefficient of 1, S2 is 0, and B is actually this right-hand side, which is 2, okay? And then S2, now talking about the second constraint, we have 1 minus 1, all right? And then S1 is 0, this is minus 1, and the right-hand side for that is equal to 1, and we can have our Z, so that's just for X1, so we have minus 1 and 0 all the way. So that's the initial simplex tableau. And how do you know if you need to iterate, basically? How do you know? So the way to know is check this Z row. And for the Z row, you discover that there's a negative place there. You have a negative value, which is this minus 1. Okay, you have a negative value, which is that minus 1. So that automatically tells you that X1 is coming to replace something. For currently, we have these two basic variables, right? And these are the two non-basic variables. So it means that X1 is definitely coming to replace one of the two basic variables. And how do you know which one it is coming to replace, right? Then in that case, you move on to have a ratio test. Okay, you have to do a ratio test. That means 2 divided by 0, 1 divided by 1. So 2 divided by 0 is undefined. And whenever you have that kind of situation, you have to avoid it. All right. So it is undefined. So we can't divide by 0, right? Normally. So, and then you can have the other one, which is 1 divided by 1, which is 1 automatically. If you even look at infinity as a very large number, right? So it automatically means that x2 will leave the s2. So this is the smallest value now. So see this now. So it means that s2 will leave. So x1 is coming to take the place of s2 naturally. That's just what that is about. Okay, so s2 will leave the basis and x1 will enter. So in that case, we now have our pivot at the intersection of those boxes. So this is our pivot now. So that one is our pivot. Interestingly, it is 1, and I mean, there's nothing really we have to do. Okay. So the pivot is actually 1 in the second row, second column. Okay. Let's see. Yeah. So perform the pivot operation to update the tableau. So, okay, yeah. So we already have 1 there. So the only thing we just have to do now is to make sure that every number above and below it is 0, right? So now we have 0, 1, minus 1, actually, and then 1, minus 1, 0, and then we have 1, 0, 0, and then this is 0, minus 1, 0, and lastly, we have 2, 1, 0, like that. So you have row 1, row 2, and row 3. Again, the pivot is this one. Okay. So that's the pivot. Now we need to so this is the only thing we need to change now. This minus 1 has to become 0, basically, because this one is already 0. So there's nothing else we have to worry about in that case. So we can go and say that the new the new row one, the new row one remains the new row one remains the same as the old row one. The new row two remains the same as the old row two, but row three is going to be different. So the new row three is going to be the old row three plus plus the old row two. So that -1 plus 1 can give you 0 because we actually need that to be 0. So if you do that now, see what happens. So we have 0, 1, 1, 0, 2, and then we have 1 minus 1, 0 minus 1, 1. And here we have -1 plus 1, 0. 0 minus 1, that's -1. 0 plus 0 is 0. 0 minus 1 is -1. 0 plus 1 is actually 1 also. So we have, okay, so now if we bring back all those things, all right, x1 is coming to replace s2 based on what we have done now. So we have s1 and x1, all right? We have s1 and x1, and this is our usual z, okay? And then, of course, this is x1, x2, s1, s2, and this is b. Now, so this is more or less like the tableau again. So the question now is, do we have to keep doing this? Because if you check this place, we have -1, -1. So it looks like if we do this, if we keep going on like this, we never end. All right. And don't forget, we're talking about unboundedness. So let's make some observations so that we don't have to continue forever and ever. Imagine you started with only one negative and now you have two. That's a bad sign, right? Usually, when you start with one, after one iteration, you should have none again. Or when you start with two, after one iteration, you have one left. And then you do that one, then you have nothing left. But now one has turned to two. So that's a sign for you already. So if you look at the new tableau, right? So looking at the new tableau, okay. So first of all, you see that the coefficient of x2, this is x2, right? The coefficient of x2 is -1, okay? The coefficient of x2 in the objective function is this. You can see it's -1. So the coefficient of x2 in the objective row, that's the z row, in the objective row is -1, okay? It is actually -1, just like I've pointed out here, right? So what that simply means is that increasing x2 reduces the objective function. It reduces the objective function. That's one thing. So it has a negative impact on the objective function. But then see the second part now. You see that the coefficient of x1, is now 0. Okay. So look at the coefficient of x1 in the objective function. So it's now 0. Okay. What does that tell us? The coefficient of x1 is now 0 in the objective row. In the objective row. Okay. So indicating that no further increase in x1 is possible. Is possible without violating constraints. Is possible without violating constraints. Okay. So we have that going, right? Now see, however, the variable x2 can still increase indefinitely while maintaining feasibility. Because of course you can see that x2 does not impact the objective function, as you can see that the objective function itself is just z equals x1. All right. So x2 has no impact on it. So if you keep increasing x2, no problem. However, the variable x2 can still increase indefinitely while maintaining feasibility. While maintaining feasibility. So this suggests that the objective function, that the objective function, the objective function z can keep increasing as x2 grows larger. Okay, no impact. As x2 grows larger without bound. Without bound. And without violating the constraints. Therefore, the solution is unbounded. The solution is unbounded. So if the solution will be bounded, it means that x1 and x2, they're actually within a particular range. Okay? So therefore, the solution is actually unbounded, right? Okay, I mean, we can make more points, right? We can actually make more points as a matter of conclusion. So in conclusion, in short, right, we can actually say that the linear programming problem, or I mean LP for short, right? The linear programming has has unbounded solution, meaning meaning the objective function, the objective function z equals x1 can increase indefinitely, can increase indefinitely. So this is because the feasible region, the feasible region is open-ended in the direction of increasing x1, and no other constraints limit this direction. Okay, so that's the idea of unboundedness. I mean, at the end of all these videos, I'm going to write a Python code to show Python code for each of them to show that these problems are actually what we claim to be that they are. All right. So if you have not subscribed to this channel, be sure to do that right away because you have a lot more coming your way. And of course, hit the notification bell so you can always get alerted each time a new video is released. Comment also, let me know if you have a problem you want me to solve, or you have a topic in maths or Python you want me to teach as much as it lies within my power, especially in the areas of scientific computing in Python or anything mathematics as much as possible. Then, of course, you want to comment. Okay, yeah, that's commenting, right? You also want to like and share so that more people can have access to all this great learning. Till I come your way again, keep optimizing. Bye.